Jeremiah's presentation will describe several items that Jeremiah has had success with for blind students all over the United States. Jeremiah has taught mathematics at Butler University since 1966. He was the fourth and last editor of Wordways, the Journal of Recreational Linguistics, and has attended all gatherings for Gardner in Atlanta. Also, he has exchanged original puzzles at many international puzzle parties all over the world. Perhaps the most famous is his November 1996 New York Times crossword puzzle that predicted the winner of the presidential race that year. It was one of editor Will Shortz's favorite puzzles.
Yes, well, thank you very much. I'm here with my colleague, Matt Maurer, and my wife, Karen, who helps me a lot with all this stuff. And I want to give you one example of the kind of thing that we do for the blind with this puzzle here. This is something that you can easily draw, and I'm going to give you a problem to work on that maybe you can solve in a few minutes. Draw the star and then put the 5 interior links on there also. And this star occurred, and of course you can see how it is for the blind. They can feel these things, these nodes, and they can feel the rods between them. This star occurs on the Egyptian pyramids, for instance. And it also occurs in this 1859 book with a different kind of thing than we're going to do. It's an example of puzzles as trees, 5 in a row, and trying to get the 10 trees in 5 rows of 4 each. And this is one of the solutions to the puzzle. That was in that 1859 book. The pyramids, that we don't know what was happening on those. But here's what I would like to do for you. I would like to show you a move here, and that you can write this out on a piece of paper and maybe try this. You take a token, start on an empty node, jump in a line, and place the token on an empty node. You can start anywhere you like on an empty, jump in a line, filled or not, and place the empty. And then you try to say, do here to here, and see if you can place the maximum number on nodes, and the maximum will be 9. I once gave this problem to a class of 20 honors students, which are very astute people, and in the entire hour they couldn't do it. I will show you later how to do it, and we'll see what happens. We're also going to use this particular thing later also, and I will soon show you what else we're going to do at the moment. Many of you perhaps can see this book. It's called Tribute to a Mathematician, and maybe you can see this. Martin Gardner, myself, and Tom Rogers. Tom Rogers, the late Tom Rogers, was a person who started the gatherings for Gardner. In that book, we have an article that's called Configuration Games, and they are all kinds of games that we can do for the blind. And I want to show you some of those now. One of the things that happens is we've had great success with the blind students in doing N3 games, which are the following kind of configuration games. And they are N equals 7, 8, 9, or 10 is what we have done for them. At any rate, here's the kind of thing that happens. We'll look first of all at 9-3 games, and let me tell you something about those. There are going to be 9 nodes and 9 lines. Each node is on 3 lines, never repeating any 2 others that are on the line. There's only going to be 3 to a line and stuff like that. Let me show you an example of something like that. Here's an example of one such game for the blind. And here's what happens here. We don't have lines on this, and we have 3 circles. There's a small one, there's another one, and there's another one. We have 3 lines, and we also have 3 different nodes. We have 3 of this little star-shaped one. We have 3 square-shaped ones and stuff like that, and things like that. And the game is to do the following. 2 people play the game, and we, instead of like ordinary tic-tac-toe, we don't give the first player an extra move. So each player has only 4 moves. If the first player doesn't win in 4 moves, he loses. It turns out that most people would prefer to do the second when they first do this, but actually the first person has an automatic win for this, other than the ordinary tic-tac-toe on 9 things that has the things like that. And we have, and I will show you how to play this after a little while, but that has a move for the first player, and the second player can do something like that, et cetera, like that. That's 1 9 3. And there happens to be 3 9 3s. And I will show you another one. Here, the 9 things are going to be any row or any column or any shape. And first can have 4 moves, second can have 4 moves, and first can win this by getting a row, a column, or a shape in 4 moves, and second can't win. And as a matter of fact, when I play second, I usually can win. And once again, the students in these classes can't figure that out. We'll see why after a while. But I want to show you a different version of this. Let me show you this one. This one is 9 nodes again. And there are 9 triangles rather than lines, and whether they're circles, lines, or shapes. Here are the triangles. At each node, there's a small triangle and a larger triangle. So there's 2 at each corner. That's 6. And then we have triangles that are circles or hearts or stars for the 9. And once again, 2 players play this game. And of course, the blind can play this because, as you can see, they can feel these things. And the first only has 4 moves again. The second, of course, has 4 moves too. And if the first doesn't win in 4 moves, he loses. But this is a forced first-person win. Let me show you something about it. Here are the 3 different 9 3s. This is what we call Pappus, because Pappus did this in 300. He's a Greek geometer in 300 AD. He put 2 lines and drew this hexagon on there. And where they came across here like that, and had this other 3rd line. You notice that on this one, the 3, there are some, there will always be on every one of these nodes 2 other nodes that don't hit it. This is a different one. This is a different one. Now, as a matter of fact, this is one of them that's on that. And I want to say to you that 1 misses 6. It's not on a line with 6. It's not on a line with 5, I guess. Where's 5? Right there. 1 misses a line with 6 and 5 and stuff like that. This is what I call the misgraph of the thing. 6 also misses 2, 2 misses 7 and stuff like that. As a matter of fact, this is a second person win, because if whatever the first person takes, 1, 2, 3, 4, 5, 6, 7, 8, or 9, if he takes 1, you take 2. If he takes 2, you take 3, and so on in order, and then play rationally, he can't win in 4 moves. He could win in 5, but he can't win in 4. This is the only game that we are going to look at where the second person can win. Now, this is another one. This is one of the other kinds of things. The misgraph of it turns out to be, instead of that 9 in a circle, it turns out to be a 3 in a little circle and a 6 in a little circle, which means that no matter what lines you choose on this one, can't be on that other one. And then finally, on this last one, the misgraph is 3, 3, 3. For instance, the 2, 9, 6 don't hit on a line. 7, 1, and 4 don't hit on a line. 5, 3, and 8 don't get on a line. So we have misgraphs here that will tell you why there are exactly 3. Here the misgraph is 3, 3, 3. The other misgraph is a 9, and the other misgraph is a 3, 6. Now, every one of the puzzles that I'm going to show the blind here turn out to be one of those 3, 3, 3s. Let me show you on this one where the misgraphs are. Look at, I mean, there's only 2 types of moves here, a corner move or an interior move. Look at a corner. What does it, where are the 2 things that miss it that don't form a triangle with that point? It turns out to be the opposite pair. This and these 2. This, and this are, that's a 3. Every corner is like that. So that turns out to be a 3, 3, 3. It is not the same drawing as with lines, but it is the same play of the graph. And I want to show you some things here on this. For instance, suppose we first plays here. Let me show you how first can always win. If the second plays in the misgraph of that, you must play in the other part of the misgraph, no matter how the other one plays. Like for instance, he might play here, and let's see, he's going to form this triangle. So I play here, he has to play here, and then I play here and win. Now, no matter how he does that, first can win. Now, if I instead play at that corner and he doesn't play in the misgraph, he plays there, say, what I do is force him to play in his misgraph, and he's played on that circle there. So what I'm going to do here, I play here, he plays here. Well, I could force him to play here. That's in his misgraph because that's on a triangle. I play here, and I'm threatening either this triangle or the big triangle, and he can't stop both. And no matter what happens there, let me rephrase what I just did there. If he plays in my misgraph, I play the other one in the misgraph and can win as first player. If he doesn't play in my misgraph, I force him to waste a move in his misgraph and can win as the first player. Now, as a matter of fact, that works in this one as well, or this one. Let me show you the misgraphs here. Remember on this one, there was every row or every column or every shape. Well, let's find the misgraphs. These 3 are not on any common row or shape or column. So the diagonal there is a misgraph, and that's a 3. This, and this, another split diagonal, is also a 3 in the misgraph. And then finally, this last split diagonal is a 3 in the misgraph. So once again, I can win this game as first by playing anywhere on here. And if he plays in my misgraph, I play the other one in the misgraph and win. Just like that other one was. Now, let's see. It's a little harder to see the 3, 3, 3 on this one, but let's look at this point here. We don't want anything on that row or that column or that shape. So this misses this, misses this. Those are on different lines, different circles, and different shapes. And that happens 3 times. So it's a 3, 3, 3. And once again, I play anywhere. And if he plays in my misgraph, I play the 3rd one in the misgraph and then go and before win. I don't have those others on there, but I do have other puzzles here that will work. For instance, there's only one 8, 3. And here it is in triangles. There are 8 nodes, 3, 3, and 2. And there are 8 triangles, 4 small ones in the corners, and then 4 shapes. This little circle, and this circle, that's a triangle. This, the heart is a triangle. And then this other little thing, the smaller hearts, smaller heart, smaller heart, smaller heart, smaller heart, smaller, are 4 more triangles. And this one, first, each of them have 4 moves here because there's just 8. First can play anywhere. Let's suppose he plays here. And second can play anywhere he likes. The misgraph on this thing, the misgraph of this one are always in pairs, and the opposite don't have a triangle in. So there's 4 pairs of 2 in the misgraph. If he plays in my misgraph, I play anywhere else and can win. If he doesn't play in my misgraph and plays somewhere else, I play in his misgraph and now win. And it's a little, this is not such an easy puzzle, but you can see that it's also done for the blind because everything he can feel and see, or he can, or not see, but feel it. And for instance, if he starts going here, and that forces me to block him, but then you see that I have a double threat here. I have either here or I have here to get the big trial. The heart triangle. Or not the heart triangle.
The little heart.
Yeah, the little heart triangle. And he can't stop them both. And that's a tougher than it looks, even though it's very quick. We have other kinds of puzzles beside those symmetric ones. For instance, this particular one here. This is a drawing. This is the Schlegel drawing of a cube octahedron. You take a cube and cut off the 4 corners. Now, I hope you can see the colors. I have a little color blindness, but there are blue 4-sided things, and there are 6 of those. 1, 2, 3, 4, 5, and the outside is 6. Those are the 4 corners of the cube, 4 surfaces of the cube. And the yellow ones are the corners that are cut off of the octahedron. So this is called a cube octahedron. The cube is the blue parts and the yellow is the octahedron part. Now here's what happens here. We can easily show that the blind can use dominoes because they can feel what's happening. And here's what's going to happen. This is a game that 2 players can play, or it's a puzzle, and we give them 12 pieces to fit on the nodes. And of course, they can feel all this. Like for instance, here's a 1, 2. I'm going to tell you that what I'm going to do with this. I'm going to put it on a node, and on every node that's connected with a line, I want it to have a number in common. And let me just say something here. Let me put this one here. So I see a 1, 2 there. There must be a 1 or a 2 there, a 1 or a 1 or a 2 there, or a 1 or a 2 there. Let me just see something else here. Let me first of all, before I do this, I have the 12 pieces that I have are 4 ones. So if I'm going to put a 1 here, I'm going to have the ones connected with 4 others. And I'm going to say to you that I'm going to, well, that's a 1, 2 there, isn't it? I choose to do this. There are 4 2s also. And here they are, 2, 6, 2, 3, 2, 4. Notice 2, 5 isn't there. And by the way, on the ones, 1, 6 isn't there. And there's going to be 4 3s, but the 3, 4 is not there. So in other words, if you think about it, 1, 6, 2, 5, and 3, 4 are the opposite sides of a die. Let's see, the way I've got it going here, the middle will have to be 6s. The outside would have to be 1s. So the 1s are going to go on the outsides because the 1 is supposed to be all the way around here. And we got 1, 1 there. Let's see, 6, 1, and then we go 2, 3, 5, 4. So the 2s go, so I can see, this is what we don't tell them, that this is from a die, because we don't want them to know this. They can play a game here with 2 people when they got to put things together. They could put this together like this if they wanted. That won't work very well, probably. But the 1s have to go outside. And let's see, I have the 2 here, the 5 here, let's say the 3 here. So I must have if this is going to be a 3 and the 1 has to be outside, this must go 1, 3 here. And this is going to be the 5, it's opposite to 2. So I put a 1, 5 there. And then the other one, 1, 4 there, because the 3 is opposite the 4. And now I can do all this kind of thing, I guess. Let's put the 6s. There are 4 6s, and the 6s have to go in these interior ones. This has to be a 6, 2, because that's going to be the 2. This has to be the 6, 4, because that's going to be the 4. This has to be the 6, 3, because that has to be the 3. And this has to be the 6, 5, that has to be the 5. Now we have 4 more to place. And you'll see this is a 2, 3. So where's that going to go? It's going to go right here, because it goes with the 2 and the 3. This one is the 4, 5. So where does that go? It goes right here, because it has to be with the 4 and the 5. And then we have 5, 3. That must go here. It must be with the 3 and the 5. And this must be the 4, 2. So you can see that everything on a line has 1 in common with this. And we don't tell them, the students, that this is a cube octahedron. We just tell them, place it on there as a puzzle so that everything has a common number in there. And then also as a game, they can play this. This is not a symmetric configuration. I want to tell you about something that Martin Gardner wrote. This is a 1959 article in Scientific American. It was one of his first articles, Martin Gardner, that is. And it discussed something by Leonard Euler from the 18th century. We have versions of this that we do on a 4x4. We have pieces that similar to what Martin Euler did, that are suitable for the blind. By the way, this thing has raised little documents that can happen here. We have pieces like the following that have 3 different situations. They have a center number, like here it's 1, and they have 2 shapes. Here's a different shape, different center number, and different shape like that. I have 16 of these things, and I have 4 of each big shape and 4 of each small shape, and the numbers 1, 2, 3, and 4. And you're supposed to put these on here so that every row and every column has different numbers on them and different shapes. Now, this is what Leonard Euler called Greco-Latin magic squares. The diagonals can't be made magic. So these are what some people might call semi-magic things. And we give this as either a puzzle for the students to do or as a game that two people play that are blind. They can easily feel all parts of this. For instance, here are the 4 big heart shapes. Is that heart? Yeah. They have to appear, the hearts have to appear in a different row in a different column. Here's what we do on this. Place on, this is, we don't tell the students this, they have to figure it out. No. So here's, I place one apple in the corner. I make a night move and place the other apple in there. That means that apple and that apple are not going to be on the row or in column together. Then I continue the night moves, placing it at that, and then I continue the night moves playing it here. That makes all the big heart shapes on different rows and columns. And then I go say to the stars or something like this, this is going to be hard to do. There's 4 stars, and I could put the stars in here, and I'm not going to complete this because it's just too hard to do. I can't put the star here because the 3 would be in the same thing. I can't put the 4 star here because the 4s would be in the same thing. But I could put a 2 or a 1. But I can't put this one because the center shape is the same. So I must put a different one here. So I can't put the stars there at all because they're going to conflict. So I put, say, one of these other things in here. You can see how hard this is going to be. I want to show you a completed set. This has the same situation. And it also, this is not for the blind, of course, but this is just to show us what happens here. Let me show you that everything is on a square, so that means nothing. But the 3 things are color, interior shape, and dot. So let's look at the 2s. These are the 3s up in this one corner. I jump with a night move, with a night move, and a night move. I look at the 1s. I jump with a night move, and a night move. I do the 2s. Night move, night move, night move, and I do the 4s. Night move, night move, night move, and night move. And what happens here is that works for this. Every row, every column has nothing in the same. Everything is different. The diagonals, however, are all the same. Like here's the same, all the yellows. Let me show you one more thing just for the heck of it. This thing back here again, and show you that this 11-3, oh, they're not going to see that. This could be treated as an 11-3, this thing that we had at first, because there are 10 nodes and there are 10 triangles. For instance, on every point of the star, there's a small triangle. So that's 5 triangles. Then the center plus 2 edges are a triangle, bigger triangle, point, bigger triangle here, bigger triangle here, bigger triangle there. So there are 5 of those interior bigger triangles that are with the outer things. So there are 10 triangles in all. And this is a 10-3 thing. It turns out that the symmetric configuration, we don't have time to play it, I guess, but here's what happens. If you take one of these interior points, its misgraph is the outside triangle here. Every little interior point misses an outside triangle. If you look at the outside points, its misgraph turns out to be one big one here, one big one here, and a small one. This turns out to be the same as this 10-3 with lines. And this has a, no, they can't see that.
Yeah, that's. It's lined up as best.
This is one of the 10-3s. This particular thing misses this line. This particular thing misses this line. This particular thing misses this line. Everything misses a line here. This turns out to be in lines with a 10-3, the same as that star did for a 10-3. We don't have time to go through all that, and it's a mess here now. So I guess we have to go back to questions now, huh?
First question that we had back in the beginning of the presentation came from Julia, and Julia asked, are we pretending to be blind? And I'd like to sort of piggyback onto that, because I was thinking something similar at the beginning, where I was trying to understand the activities, and I was wondering if I should be closing my eyes as I was trying to learn them, if I wanted to explain them to somebody else.
Well, I think explaining it, you can do it. Most of the people will have vision, so you could probably just do that. Obviously, you could close your eyes if you wanted to, and you could then have to feel everything. But then all your people that you're trying to explain it to would have to feel it's same thing too. So it's better just to do it visually, I think.
Got it.
And if we're doing it to one blind person, then he would have to do it by feel.
Got it. And Arthur asked, back when you were had up the game that was on the triangle, I think, Arthur says, in normal tic-tac-toe, the edge squares are weak because they belong to only 2 lines, whereas the corner squares belong to 3 lines each.
They all belong to 3 lines.
So that's exactly what Arthur was asking, because Arthur was saying in normal tic-tac-toe, even the center square belongs to 4 lines. So Arthur asks, in these variants, are all the squares the same strength?
They're all the same strength.
Excellent. All righty.
Every square is on 3 lines, and every line has 3 nodes on it, or 3 triangles, or those other things, the lines, circles, and shapes.
Thank you. And Roderick asked, do the triangles without lines count, such as the 3
No,
hearts?
it has to be on the nodes.
Well, we're talking about, like, for instance, this triangle.
Okay, for instance, that is not a node in the middle. The thing in the node in the middle there is not a node, so that is not part of any triangle. There's only 9 triangles there. The small and large in each of the points, and then the shapes, the 3 shapes: circles, hearts, stars. So there's only 9 triangles. Even though, I mean, obviously this little thing is a triangle, but that doesn't have a node on it. So it's not a triangle. This is a triangle. This is a triangle. You have to connect nodes only.
Roderick also asks, is the circular game equivalent to the square tic-tac-toe-like game?
They're exactly the same. The square and the circular one are exactly the same because their misgraphs are 3, 3, 3. Misgraphs on this thing are 3, 3, 3.
So they're all equivalent.
So all of these are the same game. They look different, and they are not isomorphically drawn, but they are isoagonic, maybe you could call it. The same game is played on them.
So I don't see right now any more questions that have come in from Jeremiah. And I want to thank you, Jeremiah. This was incredible. You got my brain thinking in ways I never would have thought of to think before. And I'm going.
Let me do one last thing for you on
Sure.
this star.
Absolutely.
On this star thing again.
Thank you.
To get all 9 on there, what you must do, start anywhere, jump one and leave it. And then you must fill the one that you started with. Like that. And then we started with that one. So I go to this opening, jump and fill. Then I start with this opening, jump and fill the one I started the other one with. Then I go to this opening, jump and fill and start with that one. Then I go jump and fill. But anyway, I can do that just by the key there, in case anybody wanted to try that, jump and fill, and then fill the one you started with the jump on every time, and you can put it on the 9. And that's what the students couldn't get in an hour, which is fine. That's just what happens.